Today's topic is quotient space. Let V over F be a vector space and W is its subspace. Then we can define left coset for alpha belongs to W. This is defined as S1 equal to alpha plus beta such that alpha belongs to V and beta belongs to W. Sorry, this should be alpha belongs to V. So this is called left coset alpha plus W, or this is left coset generated by alpha and W. Also the set S2 defined as beta plus alpha for alpha belongs to V and beta belongs to W is called right coset W plus alpha. That is, it is right coset generated by alpha and W. The vector space denoted by V star of all cosets in V over F of a vector subspace W of V is known as quotient space. Of V relative to the subspace W. So quotient space by V star, and it can be also written as V bar W. V bar W represents the quotient space of V relative to its subspace W, and it is defined as set W plus alpha for all alpha belongs to V. Now there is a theorem. If W be a subspace of vector space V over F, then the set of cosets of W in V form a vector space over F. So this set, it means this set form a vector space over F, and this set is called quotient space of V related to W. So this set form vector space over F with the operation of addition and multiplication defined as W plus alpha plus W plus beta is equal to W plus alpha plus beta for all alpha beta belongs to V. In same way, A is scalar number, A multiplied by W plus alpha is equal to W plus A alpha for all A belongs to F and alpha belongs to V. So under this addition and scalar multiplication, this quotient space is vector space. Now first we have to show that these operations are well defined. Now for this, we know that W plus alpha equal to W plus alpha dash. For alpha, alpha dash belongs to V, and W plus beta equal to W plus beta dash. For beta, beta dash belongs to V. Now W plus alpha equal to W plus alpha dash implies alpha minus alpha dash belongs to W. In same way, W plus beta dash implies beta minus beta dash belongs to W. So here we have this belongs to W and this belongs to W. This implies alpha minus alpha dash plus beta minus beta dash also belongs to W, since W is a subspace, or subspace is itself a vector space, and this implies alpha plus beta minus alpha dash plus beta dash belongs to W, and this implies W plus alpha plus beta is equal to W plus alpha dash plus beta dash. So the addition operation of the set of all cosets is well defined. If alpha beta belongs to the set, then alpha plus beta also belong to the set. In same way, we can prove that scalar multiplication is also well defined. For this, we take alpha minus alpha dash belongs to W and C belongs to F. So this will imply C alpha minus alpha dash belongs to W, and so this is C alpha minus C alpha dash belongs to W. So this implies W plus C alpha is equal to W plus C alpha dash. So scalar multiplication is also well defined. Also we can see here how this W plus alpha plus W plus beta equal to W plus alpha plus beta. Now if we take any element alpha dash belongs to W, then we can have element of form in this alpha dash plus alpha plus beta dash plus beta. Now again, since alpha dash and beta dash belongs to W and W is a vector space, then alpha dash beta dash will again belong to W. So this will give the element of W. We can write it as W plus alpha plus W plus beta is equal to W plus W plus alpha plus beta. Now here alpha and beta are the elements of V, and if we consider these two, as I told, W is vector space, so if we consider these two, this part, then this will again give the element of W. So this is equivalent to W plus alpha plus beta. In same way, in the scalar multiplication, here if we break this, then we get AW plus A alpha. AW will give again the vector of W, that is AW will give again vector space W. So we can write this as AW plus alpha equal to W plus A alpha. Now next we prove that this set will satisfy all the properties of vector space with this addition and this multiplication property. Now first we prove closure property. For this, if we have alpha beta belongs to V, then V is a vector space, so we have alpha plus beta also belong to V. And then W plus alpha plus beta belongs to V star. So our set is closed with respect to the vector addition. Second, associativity. For all alpha, beta, gamma belongs to V, we have W plus alpha, W plus beta and W plus gamma belongs to V star. Now we can write this as W plus alpha plus W plus beta plus W plus gamma so using addition property here, we have W plus alpha plus beta plus W plus gamma, again using the defined addition, vector addition here. This is W plus alpha plus beta plus gamma, and this is vector of vector space V, where associative property holds. So we can write it here W plus alpha plus beta plus gamma, and again we can write it as W plus alpha plus W plus beta plus gamma, and this is W plus alpha plus W plus beta plus W plus gamma. So in this way we can see that associative law holds here. Next, existence of identity. Now if 0 is vector of vector space V, then we have W plus 0 plus W plus alpha equal to W plus 0 plus alpha. So again using identity property, this becomes W plus alpha. So we can see that W plus 0 is identity element in V star. So W plus 0 is identity in V star. In same way, the existence of inverse. For all alpha belongs to V, we have minus alpha belongs to V. So W plus alpha plus W plus minus alpha, this will be W plus alpha plus minus alpha. So this is W plus 0. So you can see here that for each element W plus alpha, there exists W plus minus alpha, such that when we add these two, we get the identity element in V star. So we can say W plus minus alpha is additive inverse of W plus alpha. Now commutative property. For alpha beta belongs to V, we have W plus alpha, W plus beta is equal to W plus alpha plus beta. Now since commutative law holds in the elements of V, so we can write this as W plus beta plus alpha, and this is W plus beta plus W plus alpha. So commutative law also holds here. Now next, for all alpha belongs to V, we have for C belongs to F, we have C alpha belongs to V, and this will imply W plus C alpha also belongs to V star. So V star is closed with respect to scalar multiplication. Again, for all W plus alpha belongs to V star and C1 C2 belongs to F, we have C1 C2 W plus alpha equal to W plus C1 C2 alpha, and again here using the property of vector space, we can write this as W plus C1 C2 alpha, and this is C1 W plus C2 alpha. So finally this is equal to C1 C2 W plus alpha. So here vector multiplication is associative. Scalar multiplication. Scalar multiplication is associative. Next is distributive law. For this, C1 W plus alpha plus W plus beta, C1 belongs to F and W plus alpha W plus beta belongs to V star. We can write this as C1 W plus alpha plus beta. Again using the property of scalar multiplication, this is W plus C1 alpha plus beta, and this is W. We can apply distributive law here. So this become W plus C1 alpha plus W plus C1 beta. So finally this will be C1 W plus alpha plus C1 W plus beta. And in same way we can also prove C1 plus C2 W plus alpha equal to W plus C1 plus C2. So distributive law also holds here. Now last one is existence of identity element. Now if one is identity element, in F, then we have 1 multiplied by W plus alpha. This will be W plus 1 into alpha, and this is W plus alpha. So in this case 1 is also identity element, in F for V star. So all the properties of vector space holds here. So we can say V star defined above with respect to defined addition and multiplication is a vector space.